Welcome you all in this pre-lunch session, and this session first paper title is Key Guessing Strategies for Linear Key Schedule Algorithms in Rectangle Attacks, and authors are Jiang Dong, Lingyu Chen, Xiu Sun, and Xiaoun Wang. And first author Jiang Dong, he will present this paper.
Hello everyone, I'm Xiaoyang Dong from Tsinghua University. I'm talking about key guessing strategies for linear key schedule algorithms in rectangle attacks. This work is joined with Dingyue Qin, Siwei Sun, and Xiaoyun Wang. This report have 5 parts. The first part includes some background and motivations. Boomerang attacks was proposed by Winner. They built the Boomerang distinguisher for ED with 2 short differentials in E1 and E0. Suppose the probabilities of E1 and E0 are P and Q. The probability of ED will be the square of PQ. As Boomerang tag needs adaptive chosen pretext and self-text, several improvements converted it into chosen pretext attacks, known as amplified Boomerang and rectangle attacks. The probability is reduced by a factor of 2 to -1. Later, many works are proposed to study the probability of Boomerang due to the dependency between the 2 short differentials, such as the Boomerang switch, sandwich attack, Boomerang connected table, and its improvements. In the aspects of key recovery framework of rectangle attack, we have the following 3 models. When performing a related key rectangle with linear key schedule, we find counters miss the input differential alpha point have to satisfy the following 2 equations to be a right counter. However, they may not hold due to the linear key schedule. We introduce a trade-off in rectangle attack by guessing the full KB and the partial KF to get more filters before generating counters. We build our trade-off model for rectangle attacks with linear key schedule in algorithm 1. The first step is to collect data, construct Y structures of 2 RB plaintext each. For structure, query the 2 RB plaintext by encryption under K1, K2, K3, and K4. Store them in different tables. For each of the X bit, KX, which is part of MB and M map point K1. The first store a key counter, initialize a key counter. For each of the MB plus M map point minus X bit key involved in EB and EF, do the following steps. For P1 in L1, we derive its corresponding the P2 by encryption and decryption process. For P3 in L3, we find this partner. It's also by encryption P3 and O plus alpha, and then decrypt to get P4. Then we store P1, P2 in S1, indexed by the self-tags and some internal base. This is the self-tags, and this is some internal base. And for P3 and P4 in S2, we also compute some internal base X3 and S4 by decryption from the self-tags with some kbase, and store and access H to find P1, P2 to generate the counters. Then for each counters, for each generated counters, we determine other kbase and increase the k counters. And we select the top heads in the case C, and guess the remaining kbase to check the full k. Totally, we have to guess MB plus MF and no kbase. Before generating the content, we guess MB plus MF point with k. To reduce the memory of k counters, we guess x bit kx before initialize kc. Compute the expected number of right counters. We denote it as S. The data complexity is 4y 22 RB. We have 3 time complexity as T1, T2, and T3. We will mainly trade off between those 3 time complexity. The memory complexity includes the k counters and data structure. We apply our model to cryptanalysis on Skinny. Skinny is proposed at crypto 2016. Skinny adopts the Twink framework and SPN run function. We have a few automatic tools for differential or boomerang search. Two recent models combine MLP method and CP or SPAT to determine a good boomerang distinguisher. Qin considered boomerang distinguisher and k-recovery phase as a uniform automatic tool. Based on previous automatic tool, we built a new model to determine optimized configurations for our trade-off model. We have to determine configurations for MF point, HF, H. The objective function is to minimize T1, T2, and T3. The first step is to model the propagation of cells with known difference in EF. We start from this. This is the end of the distinguisher, and propagate from X27 to the end. We introduce some binary variables such as dx fix and dw fix to mark the known differences in XR or WR. The impact of SR and SC is determined by this equation, and the impact of MC is determined by this equation. We have to model the cells that could be used to filter counters in EF. We introduce binary variables as dx filter to denote the cells in XR, which can be used to be filtered. For example, cells with fixed difference as input to the SC operation, then we get the unfixed input. Then this cell can be used as filter. We also introduced the DW filter to denote the filter in WR. For example, there are three fixed difference in WR, and then after MC, there are only one cell. And when we decryption when computing MC inverse, we have two actual cells in WR with fixed difference as filters. Before generating quarters, we have to guess partial cells to gain more filters. We define the X gas and the DW gas variables. We know the cells in WR need to know includes known cells from XR and filters in WR. Cells in XR plus 1 need to know includes known cells from WR and filters in XR plus 1. We also model the advantage H. The objective function is to minimize T1, T2, and T3. We found new Boomerang distinguishers for several versions of Skinny. For example, all the distinguisher for Skinny 128 to 384 reaches 23 rounds, which is inferred to previous 24 and 25 rounds distinguisher, but we can perform 32 rounds key recovery type, which gains 2 more rounds. We add 4 round EB and 5 round EF to the 23 round distinguisher. In omega 0 point, we collect the plate structures, and J31 act as self-text. Then RB is 12C, and MB is 18C. RF is 16C, and MF is 24C. By our automatic tool, we determine the key cells should be guessed in advance as KF point, and we get filter as HF. We set S as 1, H as 40, and X as 208, and we get a balance between T1, T2, and T3. The final time is about 2 to 355. We also applied to our model to ForkSkinny and Deoxys-BC and GIFT. Our model can also be applied to single case setting, and we give an example application to serpent. We compared those key recovery models as follows. Before generating quarters in attack 1, we guess MB and MF bit key at once. In attack 2, we do not guess any key. In attack 3, we guess only MB in EB, and our model guesses MB and partial case in EF. So thanks for your attention.
Any question, comments? Okay, then we can thank again speaker.